So I spun the bucket in a circle. Okay. Water stayed in. Okay. Any other observations? What were some other things you noticed? Yeah.
Would it slosh on the bottom whenever you go slow?
Yeah. So at slower speeds, the water sloshed around. And the inverse implication is that at high speeds it did not do that. Okay? So at high speeds it generally stayed constant. At low speeds it generally did not. Okay? And I spun the bucket in a circle and the water stayed in. All right, here's what I want you guys to do now for number 2. What I want you to do in number 2 is I want you to try to think about why. So why didn't the water spill? Why did the water stay in? Why is it that at slow speeds the water sloshed around and at high speeds it did not? So try to think about why. And use your observations to help with that. Like, I spun the bucket in a circle. That probably matters. Okay? Why do you think the water stayed in the bucket? Okay, so go ahead and answer that.
So the water falls, but it falls in the same direction that the bucket is going.
Okay, so there's some forward motion.
Yeah.
Okay? So there's some forward motion for the bucket, or for the water. What does that sound like that we just got done talking about? Starts with an I. Inertia, right? Object in motion remains in motion. So we can think of this as inertia. Now, inertia for objects in motion has a very specific name, and that name is momentum. You may have heard that before, but we haven't talked about it yet. So you don't need to use momentum in your explanation. But momentum is a little bit of a better explanation. Otherwise, you just need to talk about inertia in motion for this forward motion stuff. But Newton's law, Newton's first law, objects in motion remain in motion. Okay? So the motion has something to do with it. The water is going forward as the bucket goes around. So you were talking about gravity pulls it down, but something about like its forward motion as it goes down pulls on it. Good. That is one of the big things we're looking at. So there is some forward motion. Okay. What else? What else might explain why the water stays in the bucket? Stick with ideas from last unit. They'll help, I promise. Manny, what do you think?
The water can get enough time to accelerate downward.
Okay. That has more to do with this. If the forward motion was slower, it would have more time for the acceleration because it wouldn't have as much forward motion. But you're not wrong. Like that is a good explanation. But that has more to do with this than something else. Liz, what do you think? What else might explain why the water doesn't spill? Okay. Mm-hmm. So gravity's pulling down. Why might gravity not win? What might be another way to think about this? What else would there need to be? Not necessarily normal, but there needs to be some sort of force. Okay? So there needs to be some sort of force. In this case, that force is applied by me. If I'm not there, this doesn't work. Right? Without me spinning it around, there's no force. Okay? One other thing, how do you think this force has to compare to gravity? How do you think this force, this applied force, how should this apply, or how should this compare to gravity? No, what do you think? How should this compare to gravity? Bigger, smaller, or the same? No, just like, is it more than gravity, less than gravity, or the same as gravity? Yeah, because if gravity is going to pull it down, then whatever force is determining what the water does, that force needs to be bigger than gravity, or at least the same. So should be greater than gravity. Okay, so now we've got something. So there's something to do with its forward motion, and there's something to do with an applied force from me. Right? If we get rid of its forward motion, it doesn't go fast enough and the water spills. If I'm not there to spin it, then there's not an applied force from me and the water spills. So that is our starting point. So let's talk about the pig. Okay? Let me do the pig example for you really quick, and then we'll talk about some examples. Okay? So in the same direction. Mason in the back. Mason G, what do you got for me? Tell me something else about the pig's motion. So, same direction, consistent circle.
Yeah, I said at constant speed.
Good. I like that. It went at a constant speed. Okay. Angelo, anything else? Yeah. I could do this without the wings and it would not do the same thing. Okay, it would not be consistent. It wouldn't have a constant speed. So the wings were doing something. The other thing I wanted to point out, this one may or may not have been obvious, but the pig itself always pointed forwards. The pig always went forward. So the nose of the pig pointed forward. The nose of the pig didn't point in the circle. The nose of the pig didn't point in. The nose of the pig didn't point out. The nose of the pig pointed forward. Okay, always. Nose of the pig was always pointing forward. So here's what I want you to do. I'll tell you when to pack up in a second. Don't do it just yet. Don't worry, you'll have time. Okay, so why might the pig do this? So, consistent circle, same direction, constant speed, always pointing forward. So, it seems to me that there needs to be some sort, again, of forward motion. And again, we can think of that as inertia in motion. Now, on the bucket, that was partially created by me, spinning it around as I went. So in this case, that's going to be partially created by the wings. And we can talk about why we need the wings later. But the wings are kind of what pushes the pig forward, creates that forward motion. Okay, so we know that the pig is going forward, right? It was always pointing forward. Its wings were pushing it forward. So the question is, if it didn't go forward, because it didn't, it went in a circle, then why does it go in a circle? What's actually doing that? Well, there's a force again. So there needs to be some sort of applied force, right? We can kind of see the pig's not going to go in a circle if we don't do something to it. So what's applying the force in this case? Well, in this case, it's going to be the string. The string is pulling the pig. Now, something that's interesting about the string is it's not pulling the pig forward. The string, so if here's my pig, here's like straight down on the string, here's the pig's motion. This string is pulling up and it's pulling in. Okay? The up makes sense. That's against gravity, right? Gravity's trying to pull the pig down. So that makes sense for why it needs to be up. The in is interesting because the pig's trying to go forward, but it pulls in. So we'll talk about that more a little bit later. That also actually makes sense here when I'm applying the force. So if here's my arm, here's my hand, okay, here's the bucket. Here's the water in the bottom of the bucket. Okay, here's the motion. Notice that my force is also in. The bucket's going forward, but the force I apply is actually in as well. So, I want you to see two big patterns here. These are both circular motion examples. Both of them have some sort of forward motion. Right? The pig going forward, the bucket going forward. There's some sort of forward motion, some sort of inertia in motion, and there's some sort of force applied. Okay, whether it's my arm holding onto the bucket or it's the string holding onto the pig, there's some sort of force applied as well. And not only is that force applied, that force is applied in. Again, the up part of the string is just because of gravity. If you got rid of gravity, you would get rid of the up part of the force. So the force is in. So both of these have an applied force. Both have an applied force in. Both of them have some sort of forward motion that is continuous and constant. Okay?